loodetavasti. So we move to the next speakers. We have two speakers at the time. Claudia Pasquero. Oh, wow. Wow. Claudia Pasquero and Marco Poletto, Ecologic Studio Architects. Please, floor is yours.
Thank you. Thank you for having us. Let me share the screen.
Nice to see you all.
With you. It's great to see.
To be in Tallinn, at least virtually.
Virtually, yeah. We should be in Tallinn live soon, we hope. Okay, can you see our screen? Looks like, yeah, it's on the.
Yes, that's okay.
Okay,
we see.
Perfect. So we get going. So again, this is us, Marco Poletto, it's myself, Claudia Pasquero. We co-founded Ecologic Studio in 2005, and Claudia also runs the Urban Morphogenesis Lab in UCL in London and the Synthetic Landscape Lab in the University of Innsbruck.
Where I have a professorship since the last 3 years. The Tallinn Wet City project that we present today is part of a research project that interfaces biological and artificial intelligence for urban planning. Before that, we will go through a series of images, a couple of images of other case studies and projects we've been doing.
I mean, as a practice, I think we are recognized internationally for our research and work in the advanced integration of nature in the urban realm. Here are some examples very quickly of projects we have built in the last few years. This was in the Future Food District in Milano, the first urban algae canopy, where 2,000 liters of living cultures of cyanobacteria were grown and farmed in the urban realm. Another demonstration of the possibilities of this approach was built in Astana and is actually permanent there as part of the Museum of Future Energy. And is a dwelling, is the first permanent dwelling, in fact, that demonstrates self-sufficiency through the harvesting and farming of living organisms within the building envelope. We have also pushed the boundaries of what we can do with digital technologies today in connection with the intelligence and abilities of living systems. And this is one of our recent prototype. It's a large sculptural work, which was actually developed for the Saint Pompidou in Paris, and demonstrates how 3D printing can be used to create substratum for cyanobacteria to grow in a kind of open living sponge that can work as a pollution filtering and absorbing and remetabolizing living machine. And finally, you may have seen some of the applications of this technology called photosynthetica, which is essentially an urban curtain or membrane to rob buildings, new and also retrofitted ones, and effectively turn them into photosynthetic energy producing machines.
So today we would like to investigate how ubiquitous computing enable us to decipher the biospheric anthropogenic dimension, what Marco and myself call the urban sphere. This machinic perspective unveils a new post-anthropocentric reality where the impact of artificial systems on the natural biosphere is indeed global, but their agency is no longer entirely human. The talk explores a protocol to design the urban sphere, or what we may call the urbanization of the non-human, which is titled Deep Green. With the development of the Deep Green tool, our team is testing the potential to bring at the core of architectural and urban design research the interdependence of digital and biological intelligence. This is achieved by developing a new biocomputational design workflow that enables pairing what is algorithmically drawn with what is biologically grown. The talk illustrates a number of applications of this approach to real case study with partner cities, first of all, the city of Tallinn, but also Aarhus, and from within the framework of the United Nations Development Programme, UNDP, with many developing countries, their innovation facility funding, and the city experiment fund. The aim of these case studies is to provide local communities, city and government with the most advanced toolset to reprogram global city for a safer and healthier post-pandemic world. With the integrated use of remote sensing, big data analysis and artificial intelligence, the Deep Green tool can be deployed to assess urban vulnerabilities and find specific urban design and planning solutions to achieve immediate and long-lasting impact. Through these case studies, we will speculate on the possibility for a general applicability of the Deep Green protocol, its scalability, and possible widespread adoption. This speculation will also lead to a critical assessment of the current paradigm of urban green planning and the conceptual and practical significance of urban regreening in the current crisis-ridden post-anthropocentric reality. While simulating the capacity of living systems in the process of growing and becoming part of a new urban biodigital infrastructure, we are challenging the nature of the city itself, now understood as an urban sphere, which highlight its planetary scale and its inherently systemic nature.
So now we are going to show a couple of videos that relate to research projects conducted in Innsbruck and in London. And this gives you a kind of broader spectrum of the potential offered by these new techniques and this innovative design approach, combining biological and artificial intelligence. Later, then we will focus on the case of Tallinn, of course, which was a part of the Biennale in 2017, and we developed further in the following years. I just want to double check that the computer sound is shared as well, just to make sure that you hear the video itself. So here, as I said, it's a really recent project that demonstrates how artificial intelligence can be deployed at the scale of the city and of the landscape. In particular, here you see how two set of data coming from erosional studies on the topography and satellite monitoring are combined through artificial intelligence to begin to reveal a series of urban scenarios that appear extremely realistic, but at the same time are speculative in their nature. The video will start now.
Every year, 8.6 million cubic meters of water flow through the mountain range of Nepal. This huge hydrologic network consists of over 6,000 rivers, making up 2.7% of Earth's fresh water. It supplies over 1 billion people downstream in India and Pakistan. Besides being vital to human and non-human existence, water is the determining force of morphologic processes. Landslides, floods, water-related diseases, as well as soil degradation caused by erosion lead to huge damage to the economy and to human life. With a constantly growing population, especially in cities, the human impact on the water quality became increasingly significant. In order to rethink the strategies of how urban sprawl should take place, we have to analyze the topography from different perspectives and understand opportunities as well as risks of hydromorphologic processes. topography of the Kathmandu Valley. Machine learning is further used to translate data, for example from erosion drawings, into a satellite image. This allows me to create output images that correspond to the calculated geomorphology of the landscape. Additionally, the flow behavior of the water can be overlapped as an extra layer of information, transforming the landscape. A new distributed urban environment is generated, which entirely adapts to the hydrology of the landscape, allowing water to be freely distributed to any desired location of the landscape. This landscape considers the characteristics of the topography and distributes human as well as non-human networks accordingly.
Okay, so, of course, water, it's the main theme of this talk today. And as we know, it's also a global concern. So for us, it's important to demonstrate, and this is what this case study also is about, the global applicability of this design method. So not only a method developed for a specific part of the world or let's say developed countries, highly sophisticated cities, but also applicable to situations where water is in fact abundant, like in the case of Nepal, but where its quality has been degrading due to the impact of the city and urban development. So this technique is really about turning this upside down and showing how water is not just the source of life, but essentially can become really an element of urban morphogenesis, a force of design that for the future of our cities. Now, before we move into the case study of Tallinn, we just want to show another little example of the application of this technique, this time in London. And again, this is looking at a future scenario in which the rising sea level potentially would break the barrier of London and the flood, especially the East End, the Docklands, and the area of wetland in the east of London. Again, from the technical point of view, the study really demonstrates how the coupling of biological and artificial intelligence could work. In this case, the input to the algorithm are again satellite images, high resolution monitoring of London, C-SPAN. You can see here the Lee Valley and the Olympic Park in the center of each picture. And on the other hand, the slime mold, which I've seen at the beginning, this kind of biological living network, which we have studied in the last few years. And here is one of the emerging results from the simulation itself. I can see there is a little bit of delay in the live feed, but hopefully you are able to enjoy this video as well.
With the rising temperatures affecting the ozone layer, the glacier poles of the world are melting, which coupled with human growth and evolution is affecting biodiversity the most. This human and non-human invasive coexistence is having side effects such as COVID-19. Since the humans starting to invade biodiversity's habitat, the boundary between entities was lost. In order to reduce zoonosis and biodiversity loss, an established boundary with nature regeneration is needed. The melting glaciers, the sea level rise. Therefore, we are projecting a flooding London that surpasses the current barriers in 200 years. With this flooding, the new water volume would generate marshlands at the edges. A marshland eventually works as a biodiversity generator. Its nutrient distribution between water microorganisms that travel through the soil can grow vegetation suitable for animal species development. In order to bring the marshland's benefits to the inside part of the city, we found the proximity relationship between bird location points and green area. With the exploration, we extracted the high-density spots, marking them as the most suitable areas for habitation and reproduction. Due to the slime mold's properties to find the optimal path and its intelligence connecting food sources, the optimal locations were used as an input for experimenting with slime mold as a biocomputer. After testing the locations, a nutrient distribution network from the marshlands to the inner city was created, bringing the marshland properties to the optimal habitat location. The slime mold's new network was then applied into the London terrain, and using a generative adversarial network, we generated an eroded morphology that takes the marshland properties and redistributes them along London, thus creating the marshland city. A formation that changes with time and height, recreating a marshland typology combined with the human infrastructure. This results in a new type of interaction, whereby providing the non-human the necessary resources to be self-sustained, the bridge to the human infrastructure is reduced. This post-natural city shows a 31% growth of green area, but maintains a delimited boundary between entities. The marshland distribution within the city helps to repopulate the biodiversity loss by bringing the nutrients that microorganisms require in order to grow. After analyzing the marshland city, materials such as algae and bacteria were extracted and combined with cement to form the materials that will shape the human and the non-human programs. Understanding the entity's interactions, a fibrous programmatic structure was created with different grids according to its main user. These programs are combined in each extruded volume to create a space for coexistence. Allowing each entity to develop its own environment, each volume becomes a nest that hosts multiple entities with different programmatic activities. With the marshland city and the fibrosynthetic nest, biodiversity can find its properties to grow. At the same time, different entities coexist with a boundary that can reduce human and non-human interaction issues such as COVID-19. The fibrosynthetic nest allows human on the inside and non-human on the outside. The marshland city embraces a flood caused by climate control coexistence in a post-natural scenario, thus creating the biocoinosis nest.
So we will now go into the project of Tallinn. This type of scenario called for a broader systemic approach to urban development, as well as for a long-termism in its design approach. An example of this method can be found in the project Anthropocene Island for the city of Tallinn, developed in 2017 when myself, together with the Ecology Studio, curated the Estonian Biennale of Architecture titled BioTallinn. As part of the main curated exhibition, we developed an urban proposal for the future of Tallinn with a specific focus on the Paljassaare Peninsula, currently at the outskirts of the city.
year, Tallinn Architectural Biennale, titled BioTallinn, works on the relationship between biology, computation, and design. More specifically, the curatorial exhibition looks at the city from a non-anthropocene point of view, realizing that in the Anthropocene age, no ecosystem is unaffected by human action, and it has become almost impossible to trace a clear distinction between the natural and the artificial, between the landscape and the city, and ultimately between the biosphere and the urban sphere. My curatorial strategies is focused on the peninsula of Pagliasarre in Tallinn through a collective project which looks at the area as a case study of Anthropocene landscape. My aim is to mobilize novel form of hybrid intelligence, part artificial and part biological, in search of a new mode of reasoning and therefore designing within a complex milieu where multiple degrees of stability, instability, as well as diversity coexist. The exhibition proposes a new strategy of urban planning which operates in a trans-scale manner from the bacterial to the territorial scale. Tallinn wastewater infrastructure becomes a morphogenetic force and evolves into an urban digestive apparatus. Pathogens are remetabolized, diluted or captured by augmented ecosystem. Infrastructural networks thickened into filtering surface, which in turn fold into convoluted epidermis populated by a large amount of inhabitable bioreactor cells, which constitute the Anthropocene island of Pagliasarre. Differently from other contemporary biennales, BioTallinn aims at using a cultural event not only to present the latest development in the architectural field, but also as a platform of experimentation and design that challenges the current disciplinary boundary between science and design, as well as between research and practice. My dream is for the Biennale to be able to discuss a new paradigm for architecture, whereas design and aesthetic acquire a central stage in the current eco-political debate, where problems are not solved but interact with through a material reading of reality, and ultimately where the figure of the single-star architect will disappear to leave space to a more diffuse and distributed design intelligence.
So to go a little bit more in detail, the project started really from far high above the land, and through the digital eye of the European Space Agency satellite, the Sentinella-3. The sensors of Sentinella-3 allow us to explore the biotic and abiotic structure of the peninsula of Pagliasarre and of the entire city of Tallinn. This image, for example, is an infrared processed image which highlights the photosynthetic activity on the ground and the different type of photosynthetic organisms. And this other one, for example, is called normalized difference water index. And what that is the algorithmic processing of data to highlight the wetness of the ground itself. And because, of course, the satellite continuously monitors the area, we can study this data with, through the changes they have in the seasons and the different years, and really get a sense of the dynamic nature of this landscape and urban landscape itself. The second step is then to use this input data and process them further through algorithmic design techniques. The one you see here really is the result of a set of simulations of water flow that essentially try to read and understand the landscape in the future, in a fast-forwarding future when the rising sea level would partially flood it again. And so through these type of simulations, of course, what becomes apparent is a new nature of this landscape, very different from the one that we now understand when we visit it or when we even look at it with our naked eye. And one of the characteristics that we became fascinated about and became a central element of the project was really this idea that the landscape has its own distributed intelligence, if you like, and that the infrastructural elements such as the wastewater treatment plant could become embedded into the fabric of the landscape itself. So in other words, infrastructure and landscape could merge into a distributed whole. And if we take this concept and explore it further, that also implies redefinition of the entire wastewater infrastructure systems of Tallinn. And so we essentially would go from where we are now, with described in this drawing as essentially a centralized and rather fragile type of network, into something more like this, a distributed system where essentially the entire terrain or territory of the city becomes an active agent of remetabolization, able to essentially take what the city expels as an output and turn it into raw material and energy to feed the city metabolism. So this could be, let's say, the image of a new circular city, a new emerging circular city that essentially grows out of the remetabolization of its waste. And this technique and the current possibilities of algorithmic design allow us to zoom in even at the scale of the individual building. This is a drawing that is using a GIS map as an input, where we have every single building mapped, the road network, as well as an extrapolation of the living biotic areas as mapped with the satellites. We can then essentially draw and simulate the shortest paths connecting the flows, the emissions, the output of each building to the closest living, processing, remetabolizing piece of landscape. So this becomes really the kind of materialization of this new symbiosis, if you want, where the built environment and the landscapes are no longer separated or even antagonistic to each other, but essentially become part of a new urban form or a new urban morphogenesis. And again, these data are updated live, are updated in real time, so we can begin to understand that as a process that continuously evolved in time. And as designers, as planners, we are capable of influencing, affecting this evolution in real time. So essentially, urban planning, especially green urban planning, it's no longer a matter of top-down decision-making, but rather as almost like a process of gardening, of cultivation of this new symbiosis.
This method envisions a new urban center emerging from the processes of the city waste as some symbiotic anti-city, which would co-evolve with present-day Tallinn and redefine its urban metabolism. This proposal is now subject to further development that will be included in an exhibition opening in the Museum of Estonian Architecture in Tallinn in January 2021, as well as will be presented at the Centre Pompidou in Paris in February 2021. Currently, the peninsula of Paria-Sarre is understood accordingly to two different and conflicting ideologies. Environmentalism on the one hand, which strives to maintain the site in a state of illusionary wilderness, and commercial development on the other, which envision the peninsular urbanization into an idealized green city. While seemingly at odds in their aims, both narratives, in fact, share an ideological conservatism in their reading and understanding of the site's true nature. Our proposal challenges conservative sentiment with a master plan intended to promote a new urban morphogenesis, whereby Tallinn urban wastewater infrastructure is made to affect the biotics to substratum of the peninsula. The resulting contamination becomes a morphogenetic force, inducing an artificial hyperarticulation of the landscape and its living system, which evolve into urban digestive apparatus. Pathogens are remetabolized, diluted, or captured by augmented ecosystem, which in turn fold into a convoluted epidermis populated by a large amount of inhabitable bioreactor cells, the Anthropocene island of Paria-Sarre. The ground protocol for Pariasarre Peninsula proposes the morphological hyper-articulation of the existing landscape and its living system, constantly monitored by a satellite. The synthetic urban landscape feedback to Tallinn wastewater network in real time. Each molecular transaction has its spatial location, morphological effect, informational address, and ecosystemic value.
Here you see again some of the images that are describing the protocol in action, similarly to what we described before, but this time getting more and more focused on the peninsula Paliasare itself. And this is one of the critical, I think, drawings that highlights the point in which, let's say, the terminals of the wastewater treatment plant slowly becomes embedded into this distributed landscape system. So almost as a kind of urban roots bifurcate into the substratum of the landscape.
The articulation of the existing landscape determines direction of flow and purification. In area where the concentration of active biodigesters is high and their emission of heat and nutritious soil reaches a critical mass, new microclimates and related habitat are formed. Growing plants, insects, and birds are attracted and become active agents of urban transformation. The air protocol is ready to begin. Swarm of stick-marching building drone, capable of spontaneous coordination, just like swarm of ants, respond to the atmospheric gradients and begin the erection of a new substructure by lifting in place modular units of different size and form, each of them hosting an inhabitable bioreactor cell. Each cell is a living unit, which evolves a certain degree of self-sufficiency. A new symbiotic relationship are established among its human and non-human dwellers. This flight assembler ground scraper that you see here grow into assemblages of many thousands of units, themselves symbiotic to the building blocks in present-day Tallinn. They will be fed by the city, wastewater, and in turn, they will feed back to the city gas, food, and fertile soil. To conclude, the future of architecture emerging from the landscape of the post-Anthropocene is, for us, wet, soft, and behavioral. It is endowed with an intelligence that is distributed and embodied. Cities are evolving into intelligent superorganisms and shall become capable of searching for opportunity or coevolution within the urban sphere, such as the project you see here. Green City must be able to find untapped resources while minimizing the expenditure of energy required to accomplish the task. These will be cities hosting both human and non-human, like microalgae in the example here. New form of evolving non-human intelligence will conceive them. Within this post-anthropocentric city, the impact of artificial system on the natural biosphere will indeed be global, but their agency will no longer be entirely human. New biocomputational design workflow will eventually evolve, pairing what is algorithmically drawn to what is biologically grown in new urban microbiomes. Thank you.
Thank you. That's it for today. Thanks for your attention. I hope everything was clear and you could hear us well enough.
Thank you so much. We heard you very well and we saw everything. It was a beautiful presentation and beautiful work. Thank you so much. Amazing.
Thank you. Thank you for having us.
It is so amazing that we don't have questions. It was too amazing. But we have questions here on the spot. You don't see us, right? You don't see me. You don't see the.
Yeah, we see you.
Ah, okay.
In the little live feed, but
yeah,
maybe
okay.
I can stop sharing.
If you see this spot, then maybe Katrin, you will come here, and they will see you. They see this place. Okay.
Yeah. Shall we stop sharing so you see us better, maybe? Or
let's try.
Okay.
Yep.
Yeah.
Okay.
Do you
Hi,
see?
Claudia. Hi, Marco.
Hi, nice
Hey,
to
hello.
see you.
Thank you for really exciting presentation. I wonder if the data you used, the European Space Centre database, is it accessible for the civic use or civil use, for instance, for local governments? And together with this question, if they could use this, what kind of experts there are needed in local governments to process this information in order to make the decisions more science-based, more aware of what's happening?
You want to?
Yeah, okay.
Yeah, no, thank you for the question. Essentially, the collaboration we have with ESA is of a research nature, but effectively they provide their data to a whole range of industries and applications. And of course, urban planning is one of those. So the answer is yes, it is possible to create partnerships with ESA to make use of their data set, which are also increasingly improving because obviously new satellites, updated version of the sensors are released. So in terms of how to make, let's say, use of this data in a let's say agile way for the purpose of planning, that's kind of, let's say, the core of our work. I mean, we have been trying to develop these tool sets, not really just as a design tool for ourselves, for our own speculations, but rather as a tool set that is scalable, so therefore can be effectively deployed in an agile manner with different partners, administrations, and other stakeholders that may be involved in this level. So essentially, that is what we do with the Deep Green Project, and is also what we've been doing in our collaboration with the United Nations Development Program, to create techniques that would quickly and reliably translate this data into maps and drawings and simulation tools for urban planning, with a specific perspective of what we may call green planning or environmental planning. So how to effectively create a better integration and let's say coexistence between the infrastructure, urban systems, and the organic counterpart in the landscape.
Thank you. It's really exciting to see these not so everyday scales, like very small cell scale activities, or the planning scales XXL. Do you deal with this human scale as well, and how?
What is exciting, I think, about these techniques is precisely the fact that it enables a kind of transcalar approach. Let's say normally, traditionally, when you look at the city at the scale of master planning, you would begin to deploy a sort of general directives and then begin to apply through policy the specific cases. Here, what happens is that the overall vision is actually informed by the relationships that are taking place at the scale of the microbiome, of course, so the substratum, but also, of course, the architectural scale. So at the scale where we live and inhabit the urban landscape and our architecture. So let's say these different scalar domains are no longer, let's say, organized in a hierarchy where, the highest level decides for the smaller in a sort of cascade of relationships, but rather there is a continuous feedback loop of information that informs the overall strategy. And as I was mentioning, I think that through these kind of tools, the aim is to create a possibility for an evolving strategy. So essentially, administrators would no longer just simply, let's say, define a policy or define a direction for several years to come, but they would be able to continuously assess the effects of those policies or actions in a kind of a feedback loop that would really make any kind of strategic decision more resilient. And effectively, the human scale would be feeding back continuously at the higher scale. So it would be much more of a co-evolutionary process than what we see today.
So in the project we develop in Tallinn at the city scale, for example, we look at the green biotic network, so the whole photosynthetic structure, as well as the water infrastructure. And we combine through data the strategies with very specific drawing at the unit level, that the unit in this case could be a bush, a tree, or a housing unit, right? So some of the drawings show the overall strategy across Tallinn, but some of the specific diagrams that Marco was showing show how the algorithm operate at the scale of the neighborhood. And the two scales are simulated by a single algorithm, so they are interconnected. You can have the overall strategy, but it's so high resolution that operate at the scale of the single neighborhood, the single unit, being this a biotic element, and with biotic we intend the trees, bushes, or microalgae, anything that is photosynthetic, or abiotic, which is what traditionally is more intended as architecture, so the building and the whole art part of the city.
And, you know, in a sense, I think we are learning a lot from nature about this as well. I mean, if you think about transport networks are ubiquitous in both social and biological systems. Essentially, nature has to continuously solve the problem of reaching out for resources in an economical way without compromising the performance of the organism itself. And so the slime mold, for instance, this little weird yellow networked organism that you have seen in the presentation, is a very interesting example of that. Interestingly enough, in kind of millions of years of evolution, this organism has worked out ways of optimizing the transportation of nutrients within its network from the bottom up. So without the need for a kind of planner or an overall intelligence to control everything. This means that the organism in that sense is very resilient. Like you could cut it in half and you can chop the network in multiple pieces and it keeps functioning locally and then eventually regrows and reconnects, right? And this is something that urban systems today cannot do because they are centralized. And in that sense, they become fragile. If a flooding or an event cuts one part of the network, the whole system fails. And so in that sense, I think the fundamental interest of this approach, this, let's say, nature-inspired approach, is to find a way to reconceive urban infrastructures from the bottom up. So where the human scale, the neighborhood scale defines the fundamental unit of the system, and then a collective emerges, the collective behavior emerges in the city. But if part of the system fails, the other elements are able to keep performing and eventually supporting, reorganizing the failed element and recreate a functioning whole.
Thank you, and good luck with your research. It's anyway really exciting to see these new concepts and new tools and methods to deal with urban issues. Thank you.
Thank you. You can, yeah. We have one question online on a website. Can you elaborate on the first project you show at the beginning of the presentation, alga canopy, autosufficient model, alga curtain?
Well, we've been developing a set of prototype that look exactly at the single cell that can be embedded in the city to create an interaction between biotic and abiotic element, as well as some of the pollutant we have been producing through urban infrastructure and microorganisms that are hosted in the city. So the Photosynthetica Consortium, which is composed by Ecologic Studio, the Urban Morphogenesis Lab de Bartet, and as well as Innsbruck University, has been working on a set of photosynthetic architecture. So architecture that host cyanobacteria. Cyanobacteria are growing as a consequence of climate change. Also, the Baltic Sea has seen many blooming. But they are also very resilient organisms and extraordinary organisms. They are able to absorb many of the pollutants we produce, are able to produce biomass that can contribute to production of energy, food, and they, of course, contribute to the production of oxygen and the cleaning of the air. So we have developed multiple prototypes that go from the most innovative and morphologically articulated ones, such as Ortux, to products for facade, such as the Photosynthetica curtain. Marco, maybe you want to say more?
Yeah, I mean, I think what is obviously we are looking at the kind of aquatic life, and essentially what many people don't realize. I mean, us first before finding it out through our research is that effectively the more than half the CO2, carbon dioxide in the atmosphere is actually absorbed by oceans, not forests, through the action of microalgae. And while unfortunately the biodiversity of species on land is declining, microalgae are proliferating in this time of climate change. So effectively, they are a very resilient organism resource that we should try to understand better and tap in. So really the core of these projects and these prototypes is how to bring these aquatic organisms within the fabric of architecture at the scale of the architectural spaces we inhabit. Essentially, the system is called Photosynthetica. I invite you to check the website photosynthetica.co.uk. There is a lot of information there. It's composed of three key layers. So we call the hardware, wetware, and software. The hardware is the photobioreactor itself. It's the artificial habitat within which we grow the cultures. And as you saw from the image, we have explored different morphologies as a part of a building skin or membrane, or as a canopy, or as a sort of a thick interior.
Which is the one you can see on the back as well.
Exactly. And so these systems essentially really enable us to grow these photosynthetic organisms on building facade. The wetware is the organism itself, the cell. They are monocellular organisms. What is interesting is that because of that, their entire body is photosynthetic. So when you compare it to a large tree, for example, these organisms are 10 times more efficient in photosynthesis and in absorbing carbon because their entire body is dedicated to that function. So that makes them particularly interesting when we look at dense urban environments, or when we are concerned with the retrofitting of existing buildings. We can talk or think about wrapping them into a thin photosynthetic membrane without much impact on the existing structures in terms of weight and loads. And finally, the software element is what we may consider as the artificial intelligent brain. So it's essentially a monitoring system for monitoring all the living parameters, temperature, salinity, pH, oxygen level within the living cultures. But it's also what gives us the possibility to compute the effect, the impact of these cultures at the larger scale. So that integrates directly with the tools and techniques that we have seen today in this presentation that was focused more on the large scale. But let's say each of the dots within this urban map could be one of our photosynthetic systems becoming part of these distributed urban network. And so that's really the way we begin to understand the transcolor approach to be implemented. And of course, microalgae are one of the possible techniques, but a very promising one because of the unique nature of these organisms, their ubiquitous presence in any marine or aquatic environment, including every city in the world, essentially.
Mm-hmm. Do we have more questions here on the spot? No. I have actually a question, but the thought about your work, like I know, like many criticals could ask you this question, maybe already asked, and I know that it's like very long answer going on about that. Do we still need the trees?
Well, we are not against the trees, but we believe that it's important to integrate biological ecosystem in the city environment, or integrate the biosphere and the urban sphere. We also think that it's important to look at the biotic system as an ecosystem. So yes, trees exist and we should support their existence, but we should also widen our horizon and integrate multiple species into city, into the redesign of city, into architecture. I wouldn't even call it landscape architecture. I would call it architecture, because I think architecture should become more and more soft and biotic and integrate multiple forms of organisms. The reason why we work with algae so much is that in a dense urban environment, they are much more photosynthetic than trees, and they are very efficient in reprocessing some of the bioproduct of the urban sphere. But it's an ecosystem that we need to talk about. So it's the integration of microalgae, mosses, fungi, tree, as well as human and other form of inhabitant of the planet. So we should start to design for the non-human, also for other species like foxes, birds, and etc. So as designer, we need to stop thinking that design is to accommodate human needs, but in the Anthropocene age, design is to accommodate the non-human and interact much more directly with the non-human. That goes from the microbiotics, so from the microorganisms, to larger organisms, animal or vegetative.
I mean, if I can add a little anecdote. Well, first of all, my opinion is that we should definitely stop cutting down the Amazon and and the forest of the world. That's for sure. And if and whenever possible, reforest and replant areas that have been cut down. But when it comes to the urban environment, there are certain considerations to be made. The little stories, when we were in Astana in Kazakhstan, actually setting up our biotech hut, this biotechnological dwelling prototype you saw before. It was the time of the Expo 2017 in Astana, and the city planted 2 million trees all around the city, forming a kind of ring, sort of protective ring of the city. Now, pretty much 90% of those trees are now dead. And why? Because obviously the environment where Astana grew up is extremely inhospitable, and there were never autochthonous species growing in that area, and essentially the city moved there for political reasons, and certainly not for environmental or ecological reasons. So in that sense, obviously planting 2 million trees became very much we could say a propaganda move, which eventually I think backfired spectacularly. So I think the point of our technique, especially at the urban scale, is to inform decision makers to create the most resilient possible network of living organisms in conjunction with the non-living or the urban systems. And of course, trees are part of the equations, but the question is how many trees, which species of trees, where, how far from each other, how trees effectively can operate as a network, as a piece of infrastructure, if you want, in the urban realm, and then what other organisms, symbiotic of the trees or symbiotic of the architecture, can be brought into the mix, into the equation to create a resilient system. So that's I think our approach, trying to move away from the kind of ideological and picturesque notion of nature as an embellishment, and essentially digging deeper into the possibilities for nature to become part of a new kind of urban infrastructure, biodigital urban infrastructure, in fact.
Thank you so much, Marco and Claudia. Thank you so much. Applause.
Thank you. Thank you for having us. It was a pleasure. Hope to be able to see you there soon, perhaps in the beginning of the new year with the exhibition taking place.
We hope so. Thank you so much. Goodbye.
See you.
Goodbye.
Bye-bye.